NVIDIA invests billions of dollars a year in developing our AI and high-performance computing technology. Cambridge 1 is the fastest AI supercomputer in the UK. It's an example of our DGX SuperPod architecture. It brings together 80 of our DGX A100 systems. All our previous supercomputers had been used by NVIDIA engineers. When we built Cambridge 1, we decided to choose UK medical partners because of the amazing medical research being done there. Most supercomputers are custom built. The new breed of AI customers doesn't have experience building supercomputers. So we built one as a turnkey product. And that's where we actually started working with DDN. There are many important considerations when designing the world's most powerful AI systems. Storage is one that's often overlooked. As the data models get bigger and bigger, and the computation becomes bigger and bigger, you need more and more data. And it's not just about moving that data, it's about moving the data at the same time. The researchers, however, they don't want to be worried about the storage. They want their AI models, their data to be stored just as easily as an email is stored when you send it over the internet. In these large AI systems, hardware capabilities are just the start. The real differentiator is DDN's use of a parallel file system. And that's why every DGX SuperPod we've shipped has come with DDN storage. I never hesitate to recommend DDN. I know that if DDN can meet the demands of the DGX SuperPod, they can meet any of our customers' requirements. What I love about DDN, they're not new to high performance. They're the de facto name in high-performance computing storage. And now, by working with us, our DGX SuperPod, they're the de facto name for AI storage in high-performance environments.
Hi, Dave Lippman, Truth in IT. Welcome to today's webcast, maximizing ROI on your AI infrastructure deployments for generative AI and large language models at scale. Today's webcast is sponsored by DDN and NVIDIA. And in just a second, I am going to be handing things over to our panel today. We will be led by Mike Matchett. You know Mike. Mike is Principal Analyst and CEO at Small World Big Data, and Mike will be joined by James Coomer. James is Senior Vice President of Products at DDN, and Mike and James will be joined by CJ Newbern, who is Distinguished Engineer with NVIDIA. We expect today's event to probably go about 40, 45, maybe 50 minutes, and of course we will be taking your questions and comments in the chat room. We have staff standing by from DDN and NVIDIA to answer any questions you've got about today's content, and of course staff standing by from Truth in IT to answer any questions you might have about the video feed or the audio or anything like that. So any questions on that, please chat those in as well. But now let me hand things over to Mike and James and CJ. Mike?
Yeah, thanks, Dave. I am really excited today because we get to talk not only about the hottest topic in IT and in business in general, which is AI today, and talk a lot about large language models and generative AI in particular. But I have some stars in the field here with us today. I've got James here. Welcome, James.
Hello. Hi there.
And we're going to talk a lot about DDN and how we address that. And I've got CJ here from NVIDIA. I mean, you guys make GPUs, right?
A couple of them.
Right. So between the two of you, we're going to learn a lot about AI and generative AI and what it takes to support that at the largest of scales, and get some technical details out of this. So without stalling too much more, let's take a look, James. Maybe you could start to tell us from your perspective, what do you see is the major problem or challenge for IT and the data center folks when faced with this demanding workload of generative AI at the largest of scales?
Yeah, thanks. Well, as you know, and I think we've talked about before on previous webcasts, is that DDN and NVIDIA have been building some of the largest superpod systems for customers, for national systems, for vertical systems, and for NVIDIA's Selene and EOS systems. And during that time, obviously, we as builders, supporters of a large storage systems, been working with NVIDIA to tightly integrate and couple these things together so we can accelerate, make more efficient, particularly that right-hand side of the diagram we'll show shortly, the data center side. It's moving data to GPUs, it's making the whole infrastructure much more efficient, making best use out of the networks and the compute, and trying to remove the wait time for storage as far as possible. But during that time, of course, we got to talk to a lot of diverse customers, and we get to know the whole end-to-end AI development process. And of course, it's very, very complex, and it's getting more complex as time goes on due to new challenges of larger data, new challenges of data distribution, new challenges of having mountains and mountains of metadata arriving on the scene right through the pipeline. And then recently, we've also been seeing challenges of sharing resources, because one of the only ways organizations can access to large resources now is very quickly is through NVIDIA cloud partners, these NCPs, and that's shared infrastructure, and that brings its own challenges of security and data sharing and managing service levels, etc. So we're going to talk broadly about all these areas.
All right, and if you look at that graphic that we put up here, there's quite a bit on there in terms of all the different stages and steps in that pipeline. There's also things we need to talk about, like data privacy and security and some other stuff that comes around the edges. So we'll get to that. CJ, from NVIDIA's perspective, I mean, everyone wants GPUs now. Everyone needs GPUs. Everyone's looking for it. What are your sort of like overall impressions of what's going on at this high ends, particularly with superpods and AI today?
One of the remarkable things that's happening is just the notion of scale. That when we do LLM training, for example, you just need huge systems that have to run reliably for a really long time. And it's not just a matter of individual ingredients in a solution, but the integration of all those ingredients into a whole system. And there are a lot of things that we care about that aren't just performance, but like, where do we do which kinds of operations, and what kinds of new architectures do we need for that? There are new ingredients like data processing units or DPUs, the layering of storage, of doing work out near storage, of figuring out where you really need performance and where you don't need it so much. I'm passionate about driving zero trust in NVIDIA, and security is a major concern for me. And you just, with all these precious resources that are rather expensive, sharing them and getting the best efficiency out of them across multiple tenants ends up being a real key issue. So there's a lot of complexity in here, and we all want to make it just easy so that it just works for customers and works very reliably.
Yeah, we've talked a little bit already about the enterprise and the data center, but AI is not just at the data center, right? This is something that's going to be pervasive through computing from edge to data center and even into clouds, right?
Absolutely. And there's a lot of there are a lot of people that are asking sort of where is storage or is not storage on the critical path to being able to get things done. And there are a lot of people where working at the edge, we've talked to a number of customers where the last generation wasn't so critical, but they're looking to increase performance and sort of data acquisition rates by 1 or 2 orders of magnitude, and then storage does start to matter. So we're very interested in looking at that whole end-to-end solution and the variety of different kinds of applications and architectures.
Yeah, I've heard you say a couple times now, it's not just about the GPUs. You're being very inclusive here and talking about the whole architecture has to work, the storage has to work. It's all about the data in a lot of ways and getting data into those GPUs. So you can't do that in isolation. So James, you want to tell us about how you might go about that and what are the different tasks that the storage really addresses in that AI pipeline?
Yeah, we're going to take it in. We're going to take it slowly. I think firstly, we're looking here at the broad picture. What we want to do is take you through what's happening at the infrastructure level, and then take a look a bit more detail about how the application environment is changing in terms of moving to multimodal, moving to new models that have different ways of accessing data. So first, maybe CJ can talk us through what's happening. So we're seeing huge demands for more GPU power, more CPU power associated with it, larger memory footprints, larger fatter networks, and of course, data management and data movements to support all the infrastructure. So, at its base level, we need to cope with this huge explosive growth in the computational capabilities coming up over the next 6 months, 12 months.
So I was pointing at storage, and now the storage is pointing back at the GPU here, CJ. Tell us a little bit about how you're facing and NVIDIA is addressing this growth in requirements.
One of the favorite quotes I have of Jensen's is that sort of we only work on the hardest problems that no one else is solving, and that we sort of go and enter into $0 billion markets where there's essentially no one's been there, no one's done that before, and we go and make something possible. And so kind of one of the new things that's happening is to take a GPU, which used to be a chip like this, and is now a rack. That a rack acts as a single GPU that's integrated with CPUs as well, tightly coupled, where you have a lot of computational density to solve these really big problems. Again, for LLMs, you need to run for a couple months to train it, and it's really expensive to be able to do that. So one of the interesting things too is that you have to be able to run that reliably, and so for things like checkpointing start to matter. The failure domain now grows to potentially a whole rack instead of just an individual system. And you have to look at how that interacts with the rest of the world. Where do you put storage? How do you manage storage? How should that be layered? What are the right interfaces? How do you keep storage sort of out of the way? And as much as possible, move things to user level. Where do you move the smarts in the system along the spectrum of all the way from the backend server to having proxies throughout the system, including right at compute nodes? So there are a number of implications when you start looking at these very, very aggressive systems that can bring us these new technologies and capabilities as to how you feed the beast and how you manage that in a reliable way.
And one point for me, Mike, is that we've seen in the past other storage players saying things like you don't need this much performance, but this graph kind of points to something else, like when will you need the performance? It's a parallel file system is a beast in terms of performance, and when you've got exponential growth in terms of the capability of the CPUs to ingest and process data, the memory footprints are going up again exponentially on these curves in order to cope with these large AI models. Then storage performance, even raw storage performance, is very important. But we're going to talk a bit more about something more subtle, not the raw storage performance, but the data path, the cross-stack integration, the software pieces that help us move data more intelligently, more efficiently, rather than brute force.
So brute force. And I notice also that we're bringing in the CPU into the conversation as well, right? So we could also be talking about that. And if folks haven't got up to speed yet on SuperPODs and what's going on with that, I encourage you to go look at some of our previous videos and data about that. Tell us a little bit then about this data path. Where does it start to become a bottleneck or an optimization point where you actually have to focus on it?
Yeah, everywhere is a bottleneck, in fact, or potentially could be. And again, we're going to get into a little bit of detail now about how these models are changing, and that impacts this stuff. You'll see a few numbers scattered about, taken from various research papers about the worst case scenarios in terms of the amount of time taken waiting for data. Hopefully these are worst case and they don't want to happen at the same time. But the point is, even in ingest and data preparation, that can be a bottleneck. That when you're in the superpod world and you're running large scale multi-epoch training, then you can have bottlenecks in terms of loading the data. You've got to load the models into GPU and load those checkpointed models from transfer learning back into GPUs. The training phase in green here is like the one you want to be doing. You want to be spending all your time doing that, preferably. As far as storage people are concerned, we want to take ourselves down to the minutest amount of time and leave that time for productive training. And that's really what our job is at DDN. And then finally, this checkpoint stuff, as we said, for many reasons, including managing very large scale systems for multiple months and having very long running jobs, we need to checkpoint those things. And then finally, we have to distribute those models. But the ratios of how important these different elements are change over time, and they change as the ecosystem is changing. So for checkpointing, for example, we've been in a world which is, large checkpoints being regularly taken. We've got a customer right now who is trying to keep the checkpoint times below a small number of % of the whole runtime. Makes sense, right? Because that's wasted time. Because when you do a checkpoint, nothing else happens with synchronous checkpointing. Now we're trying to cope with that by adapting the software so we can move the data asynchronously, so the compute can continue while the checkpoint is happening. But it takes time. These models have got to be matured. So checkpointing is one area where things are changing. Models are getting bigger, but the approaches we've got to minimize the impact whilst training are also getting more sophisticated. And that's happening across this kind of picture here. And on the ingest and data preparation side, I say many of our largest customers right now, they're building massive hyperscale infrastructures because they're trying to get a competitive edge on the rest when it comes to this next generation wave of large scale multimodal models. And that means we're going to be ingesting much more images, video, sonar, radar, audio files, all these very large format files. Large language models were quite tough, but actually, look at the data we got to use for that. It turns out to be, a pile of words. When you deal with images, video, LiDAR, radar, audio, then all of a sudden that ingest, that data preparation, that data movement from edge to core, the left-hand side of this picture becomes much, much more important. And then the data load, of course, becomes a much more critical issue. So things are changing in various ways. Some things getting better, some things are getting worse. But overall, we're sitting on top of this exponential growth across the board.
Right. And so if I'm hearing this right, there's that core part where NVIDIA really plays with the GPUs and keeping them loaded and doing the training and trying to compress that time frame down. But more and more importantly, as the world moves forward, that's obviously got to grow, but it's about getting those new kinds of data, those new kinds of applications of AI that are going to look at different sources of data, pipeline properly into those. And if I'm also following along here, right, there's some efficiencies to made on checkpointing as the models are going along and they get bigger and bigger and more distributed as well. There's some challenges, some really big challenges on those storage IO parts of this diagram that are evolving and growing larger, not just the requirement to scale up the middle part of this diagram, right?
And just kind of, there are at least two things that we could drill into just a bit. One is that it's often the case that you're in a big hurry to load data directly into a GPU. So for example, if you select a model, that model load time where you're trying to get the model into the GPU can matter. And so we have some technologies like GPU direct storage that we've had working with Exascaler, that we're anticipating working with Infinia as we get with that, to be able to sort of skip making extra copies through the CPU and load directly into the GPU, so being more efficient. There are a number of things to look at in the checkpointing space. James, you mentioned that thankfully things are getting more asynchronous, so that instead of stopping the world while you wait for all the data to be archived out into some safer place, that we can basically take the data out of the GPU, stuff it in the CPU, and then let the GPU keep working while the CPU has all day long at potentially a lower service level to push it out to some place that you can get archived. There are some changes there too, where we're seeing that historically and even currently, most everyone is doing things in file format, whereas object formats are much more efficient and effective here. You don't have to open and close files and have bazillions of files open. You don't need to do read and random access. You're basically just streaming data out, and object is very good at that. There's some interesting challenges with checkpointing too, in that the way that some people work is that over a 2-month period, they'll keep all of their checkpoints and then decide, oh, the model went awry back here, so let's roll back and tweak something or other, and then have it go in a different direction from this point. And so you don't know which of those checkpoints you need to keep. And so you need tremendous capacity. So I think we're moving to a place where the writes, the saving of the checkpointing just doesn't matter, because we can hide that. When something does come back up, it does directly impact your performance. It's on the critical path because you're trying to read things back in. And so then this starts to affect your system architecture of, where did you stash that data? How can you bring it back in? How skinny is your straw getting to the storage? What happens if the whole rack went down and now you need to migrate the data to someplace else? Then having something in a central location may be favorable. If it's a local failure of where you could just reboot and bring it back up in place, then having something that's much more distributed may be favorable. And I think we as a community are still working through many of those challenges. Something that we've kind of wondered is there a place there for providing, as a neutral party, some sort of a checkpointing service that can various vendors can use, and that kind of stuff. So we haven't decided to do that, but that's kind of something that we could consider. So we're just looking at, how do we solve this as an end-to-end problem at the whole data center and cloud level, not just the individual component level.
Wow. And I just have to say, as an old-time storage guy myself, we talk about checkpointing and things. It sounds like data protection. It sounds like snapshotting. It sounds like, time to restore and recover enough. So like, a lot of these concepts conceptually keep coming back around, but now we're applying them at huge scales and more in real time, right? We got to be up to speed on that. James, can you maybe start to tell us a little bit about how we want to think about the storage architectures evolving to support these changes, these evolutions coming?
Yeah, I mean, let me summarize a little bit first, and I want CJ also to talk about the newly emerging RAG models as well. But what I wanted to summarize is, this picture is just talking about the I/O data movements. We are part of an integrated infrastructure, an integrated set of software, and there's elements here of complexity, i.e. governance. The organization has got to track this from end to end. The data is coming from all around the globe. It's got huge amounts of metadata associated with it. There's a complexity and manageability problem. There's a data distribution problem. The data is not in one place. It is everywhere. There is this core piece. It's how fast can we move the data to the GPUs, and how can we make sure those GPUs are busy all the time. And then there's a security aspect as well. So I just wanted to pause and basically pull out all those kind of important themes that we've kind of talked about, but not spelled out. Before we talk about what storage can do to cope with all these changes and these challenges, CJ, could you just give us a little introduction to these RAG models that NVIDIA's been very talkative about recently?
Yeah, so there's some interesting things when you want to train and use large language models and so on. One of the things people are worried about is sort of hallucination okay, that's cool, you're able to make this stuff up, but were you just making stuff up? One of the things that's very helpful to do is to have other context relevant data that's available. There may be a lot of it to sort of keep you on track, to keep you honest with what's going on. And so RAG can tend to help with that. So you may then, from your local computation, need to go to much larger scale in what it is you're doing. So this is RAG is retrieval augmented generation. So you may need a petabyte data lake that you're trying to get access to. So there's another trend that's happening, is that in DL training, for example, where you're bringing in images, you would bring in sets of images, you know which images you're doing everything with, and you bring all that information and you crunch on it and train on it for a while, and then you go get your next set of images. That's very easy to coordinate from the CPU. With a lot of things that are dealing with graph analytics, for example, and vector databases and vector search, it's actually each individual GPU thread that has to figure out what it's going to do, right? Which node in the graph am I going to visit next, et cetera. And every thread does that independently of all other threads. So in those cases, you want the GPUs to be able to do their own access directly to an unbounded amount of data. And so that just gets to the point where it won't fit in memory. And so now you need GPU initiated storage. So sometimes that may take the form of key value or object access or whatever that you're doing. So we have some new technologies that we're developing. So for the scaled accelerated data access is a new programming model we're exploring and doing some proofs of concept in this space. And one of the things that as that matures, to be able to also bring into the GPU data that's far away and that's very, very large in size, that's persistent, we'll need appropriate interfaces for that. So just to kind of up-level that, the new demand here is that you'll have new programming models on the GPU. Those will need to go get to storage, and we'll need to be able to have back-end abstractions that are extremely efficient, that can deal with very large-scale, fine-grained accesses with minimal overhead. And so being able to have that underlying storage infrastructure that can deal with objects and key value stores, to be able to bring that straight into the GPU is going to get increasingly interesting.
Yeah, but it's very cool, by the way, because it means that we have to change our picture here. We have to extend it. And so the whole ecosystem, this picture's done as well for a few years now, but we need to extend it, because when those models are distributed, they still need access to data with these RAG models. They still need access to these very large systems. And also the way, when you're doing the training, the way the data is being accessed has new nuances with these vector approaches. So things are getting more sophisticated, and the way AI models are interacting with data is changing, and that means the way storage integrates with the infrastructure is also changing. And that's really what we're going to talk about here.
Yeah, I think you're really going to need to come back for a whole nother discussion about this new type of evolution in the retrieval augmented generation and what that's going to do. Just to try to summarize that again from my perspective, we've got large language models, which are challenging enough for some people. The training takes a lot, and you're creating this basically vector space of attention for predicting what the next word's going to be in any sort of flowing set of computational linguistics, but it's not factual. So we add retrieval augmented generation, so the model can actually say, here's where I should have a fact instead of just making something up. It goes out to a database or a data lake or some other thing, I think is what you're saying, or a graph database, and pulls that in. And that's going to be huge. People are going to say, yes, we need our artificial intelligence to be smarter and be more fact-based in the long run. So is that a fair summary, that's where the world's going to go, and that's what we need to start preparing for?
It's a big part of it.
All right. Sorry to up-level that. Let's dive back down, Jay. So what do we see about storage architectures then? So what are you looking at having to do to support all this?
Yeah. So what can storage do as part of this extended architecture? Extended in that it's at the edge, it's in regions, and it's at the core and in clouds, right? So firstly, it can be more manageable at massive scale. Kind of simple point, but is always the target for organizations like ourselves. Collapsing infrastructure, so getting rid of unnecessary bits and pieces, just part of Jensen's mission as well, like getting to the efficiency into the infrastructure means taking away pieces you don't need, reducing, collapsing, just like the whole NVIDIA DPU stuff, we can pull this stuff together, pull CPUs and network interfaces together and collapse some infrastructure into more intelligent pieces that are going to be more efficient. The fourth bullet point here is kind of, we're going to delve down into just an example. So optimizing data paths. And we don't talk about this much, but of course, I mentioned brute force earlier on. When you source some storage and you want it to be fast enough, typically you'll look at the gigabytes per second. Now that's the gigabytes per second as measured by typically some benchmark. And it might have very little to do with the way your applications or AI models or inference models are actually trying to access the data. And that has a huge impact because it depends on the networks, it depends on the particular calls that are being made by the applications, the number of threads, all this kind of stuff. It's a huge parameter space, which means that storage performance just isn't one thing. It's a myriad of different things. But optimizing data paths is what we've been doing in general to get maximum efficiency out of the infrastructure. And there's many pieces to that, which we kind of call out here. So we're going to talk about that in a bit more detail. And then the second other major thing is managing data locality. As we've just talked about, these inference models running out in the field are going to want access to large caches of data in order to be more correct in their responses. Simultaneously, the multimodal models are going to start getting shipped out to the field, and they're going to be accessing and consuming much larger piece of data because it's no longer words, but it's images, videos, etc. So all of these things matter, and the one thing we haven't talked about in detail is a security aspect, which we'll couple into the talk track as we go through here the next few slides.
Right, because there's some interesting things here. Optimizing the data path is something that we've been doing for decades, right? No matter what we do in storage, we try to optimize the data path, and it's always an evergreen challenge. So I'm interested to see here more details about what specifically we can do on there. And data locality, I've got some questions about that when we get to that too as well. CJ, from your perspective, just to get some 2 cents in here, when you guys are looking at the superpod architectures and looking at the latest generation of GPUs, you did mention that you're starting to create some new protocols and ways to call out to storage and work with storage. Is there anything missing here, or something we should call it in specific to talk about how you work with the GPUs?
Yeah, I think one of the things that the key questions you want to ask when you look at something at a data center level is not just what should happen, but where should it happen and how should it happen. So there are a number of things that you don't particularly want to happen on an untrusted compute node. So a compute node is where the user's application runs, and that's the easiest place for them to break out of their container or VM and root the node. So if they do that, what are you concerned that they might do, and how do you contain that? And this is particularly important in a multi-tenant context. So there are things that you may wish to move off of the compute node to happen that you really want to happen securely and robustly. You may wish to move off of the compute node and into the network infrastructure. And thankfully, there's network infrastructure that's right at your doorstep, that's on the PCIe, that's right there in the compute node in the form of a DPU, data processing unit, and that can be independently controlled part of the infrastructure, the more trusted infrastructure. So that's something that you can use for acceleration and offload if it's performance that's the problem. I tend to think that security is a greater motivation of, I think as an American, I think that I'm really concerned about the security of what it is that we have. We're going to get attacked more and more in what we do. And so making things secure by default is really essential for being able to do this. I think we'll dig into that a little bit more about what do you do, how can you move things a little bit into that infrastructure, do things with great efficiency at user level, set up appropriate proxies between what happens there and the potentially far away backend storage. So there's fun things that they can dig into there.
All right. So just in the interest of keeping this moving along a little bit, let's dive in then to some of these points is in some way. You mentioned object storage, James. What, object storage is what? S3 protocols, get and puts. Where that doesn't seem to have ever been performant
Right.
this cloud storage, right? So what's going on there? How are you guys thinking about providing, basically an object streaming to this AI monster that we have?
Yeah, it's a great question. And you're right, most AI training is done via file systems through POSIX. And the fun thing is, remember POSIX standard was created, I guess, before I started in IT, but it was created and defined when you literally had one CPU with some memory and one disk. So it's not greatly applicable to the world of highly distributed data, huge amounts of metadata, strong security, all this kind of stuff. We do a great job, but actually S3 has some great native attributes that really help us manage this data distribution, manage this metadata challenge and stuff. But as you say, the problem is it's not fast. Particularly when it comes to latencies and feeding that GPU with low latencies when it's requesting data. So I've got a few slides. We're going to dive in a little bit into a bit of technology, what we're working on right now with our DDN and Infinia product. So it's a little bit technical, but not too technical. Right at the top, we've got a picture here, and we're looking at a bunch of compute hosts. So you can think of these as possibly NVIDIA DGX machines, something like that, across a network. And then at the bottom, there's DDN, some distributed storage in principle. And with S3, we've got a RESTful call. It's not RDMA accelerated. It's actually HTTP calls. And in this case, the application is doing a put of some data, maybe creating an object, a new object, and it's placing that data into some distributed storage. And then the distributed storage is going to take that object, it's going to erasure code it to protect it. Right. So that's the traditional approach we've got today. And the challenge there is that this is high latency. It thinks about put, thinks about gets, doesn't matter. These are RESTful calls over HTTPS. They're not RDMA accelerated. So they're not leveraging these offload mechanisms and TCP offload that we get in high performance computing environments. And then along comes these BlueField DPUs, the NVIDIA BlueField systems, and they change what we can do now. Now they're adding new compute resources, slightly remote from the applications, which I'll let CJ talk about that in a minute, but it's going to be great for security and zero trust, but it also adds something really interesting for us as people who build storage. And that's what I'm going to talk about first, and then we'll come back to the security aspect. So you notice at the bottom of the picture, I've slightly changed it. Our distributed storage is now, and this is the architecture of our DDN Infinia product, it's now a microservices platform, which means the whole storage service itself is combined of many containers working in orchestration across a distributed set of nodes to present and preserve data to applications. And because it's containerized, we can start to do very unusual things in order to optimize this whole architecture. And here we're still looking quite conventionally. In this picture, we've added these BlueField systems to the storage and server side, and that's going to give you the usual advantages that BlueField gives you around managing very, very large scale Ethernet networks and keeping them optimal. But also what we can do is we can take these containers at the bottom and we can start to move them over the network. So what I've done here is I've taken the S3 component of our storage service, which conventionally is in the storage servers, and I've moved them right across the network, and I've instantiated those containers on BlueField on the compute side. And now lots of very good things have happened. So A, we got more resources. We got more CPU because the CPU in those BlueField, there's many compute nodes. We got huge scale for these S3 servers that are running in these containers. We're running close to the applications, but we're not consuming the CPU where the applications are residing. So there's no impact on the applications, no negative impact in terms of resource consumption. The applications are still talking S3, they're just talking very locally. They're talking as far as the local BlueField adapter. That's as far as that data path goes. And then most importantly, now the data path, the vast majority of this data path is accelerated. It's RDMA, it's erasure coded from the client. We're taking advantage of InfiniBand and we're offloading all that packet management. So it's making it much, much more efficient. So lots of really great things are happening by containerizing the storage system. We can leverage this new DPU-driven storage architecture and gain scale, gain performance, gain efficiency, and change the data path to massively reduce latency. And then we get back to that first issue you mentioned before. The challenge of S3 is typically latency. And by using these new architectures, we can remove that challenge. We can take that latency right down to where it can be a tier 1 storage with the applications can talk to directly.
So object storage, which has been secondary storage, now becomes primary storage, and not just primary storage, but HPC class primary storage. You've exploded it. You've massively parallelized it. I can't say paralyzed, parallelized it, made it much very parallel. And then BlueField, which is a fascinating card that we've talked about, DPU cards in the past. And maybe CJ could tell us a little bit more about BlueField and what that's actually doing for this whole architecture.
Yeah. So BlueField is take a NIC and make it smarter. Don't just have an HCA, but take some ARM cores and take a bunch of accelerators and put them on basically on the wire so that you can either do stuff as it goes straight through and accelerate things that way. For example, being able to do encryption or be able to sort of bring it into the ARM memory and to operate and do data transformations on there. So one of the things that is interesting that I find as being a really compelling use model for this is in secure storage. And so we're partnering with DDN and others in this space. So the notion is that, again, if someone were to attack your storage system, there's a lot of work that happens on the compute node that you're sort of trusting to, like, let's make sure that nobody hacks that. And there are additional layers of protection that, for example, Infinia brings that Exascaler didn't have as completely or to the same degree, that are less worrisome because you're doing more checking at the back end and you've changed the architecture. But being able to have a neutral agent that's running on the DPU that basically provides the remote keys for the RDMA or the remote direct memory access so that a backend server who wants to write data directly into the CPU or GPU on the host, you don't want to just give those out to anybody, and you want to make sure that those are done in a secure way. So we're looking at being sort of a safe broker for being able to do that, so that you can take the original request from the host and execute it on a client that's running more securely on the DPU. Nothing's ever secure, right? And still be able to do additional transformations there. One of the exciting opportunities is to do things at a user level. And so Infinia is a user level client, so that you avoid some of the extra overheads of going back down through the operating system on the DPU. It's a full compute node. And one of the cool things about a DPU is that it's independently controlled in terms of its management service. So even the host doesn't control the DPU. It can't reconfigure it. It can't change security parameters. It can't open new ports or whatever. And anything that any communication that the compute node tries to have with the outside world has to go through the DPU, and the DPU is in control of that, who it can talk to, how it can talk to it. And so you can avoid denial of service attacks. You can avoid user level spoofing. You can use scheduler information to know, like, are you actually supposed to be on this node, or are you running someplace else and like have or feeding a buddy over here that's doing something malicious? A whole variety of those different kinds of attacks can be thwarted. And it creates a pretty exciting new opportunity to do things very differently in this space.
Because it looks like you can distribute some of the storage as James was telling about, move those containers from the actual storage system up. you can configure very tightly who talks to who, and you can accelerate a lot of what's going on the network. So you're accelerating network. We didn't talk about the network specifically, but that's what we're doing. We're accelerating a lot of what would normally be slow network traffic. And parallelizing. The one thing that's surprising me that I'm just learning today that you're talking about, CJ, is security, that it's adding a lot of security. I was thinking always about performance and optimization. So I'm interested to hear that. Yeah.
And if the goal we're still working through, right, to understand what the performance overheads are, but the goal is to be able to do it so that you don't pay a tax for security. Right? This is I think an essential element to anything you're doing in data centers to get security by default, so that people aren't scared of it and they don't know what's happening. They don't particularly have a choice, and the network administrators who are configuring these things can reasonably just say, like, yep, you're getting security by default. You don't know it and you don't need to care, but it's there and it's working.
Awesome. All right. Let's keep moving along here. Back to you, James. You talked a little bit about Infinia. Infinia is this new, it's not brand new, but it's a new, really thrust for DDN. It's a new kind of venture. Tell us about what Infinia really is and what it's doing for people.
Yes, so Infinia is ground up developed by DDN over the past 5+ years, completely new, right from how we store the bits on flash, right through to how we expose the protocols to applications. Everything's been written from scratch in order to tackle these challenges we were talking about earlier on. So data security, containerization, ease of use, online upgrades, data distribution, all of those things are built into the core of Infinia. It's quite radically different from other storage systems out there today. And so we've got many things to talk about and only a few minutes to talk about them. So we've covered one aspect, one aspect only. The containerization of our Infinia product means that we have this kind of unusual capability to spread the storage service across the infrastructure in new ways for better efficiency of the whole infrastructure. And the second challenge, which we talked about earlier on at the start of the presentation, was the fact that data is distributed. And we can also handle that in new ways with Infinia. As I said, we're really moving to an S3 world, particularly out here, where we're not in the data center. Right now, the superpods, the data centers tend to be file systems, and objects tend to be used at the edge and for data distribution. Now we're talking about being able to push that closer to the GPU, right? But still, we have the challenge of moving the data when it's at the edge or when it's in a region rather than the core data center. And we've got various concepts built into DDN and Infinia to help make that manageable and make it efficient. And I've just got one little example here. We have an Infinia system, and we're able to register it with a remote data set, so that when data is created in a remote data set or as an event at the remote data set, we can execute a function, and that function will do something. Probably it's going to move that data to where you want it. But we're kind of combining a bunch of concepts here, which CJ's also referred to as like storage offload functions, doing things at the storage where the storage is, rather than pulling it all across the network. So that's all part of this, and it's part of building efficiency, particularly when there's not strong networks between all the components of your data around the world.
And so, yeah, and I can see the importance of this when we were talking about our first models and the training where data could be distributed at that edge. You don't know where it is. You've got to bring it together and correlate that, and then distribute models back, right? So you've got this in and out part of that first diagram we were looking at, where it's not in the core, but it's how do we get that data, from the sources and then get those models back out to where they're going. But also we talked about that retrieval augmented generation part that's coming up fast, right? Which is to say, hey, I need to access remote data sources. I need to access data lakes. I'm going to need to do that in a highly performant way, not simply in a training manner offline. So I can see this being a big player in that too.
Exactly. It might be in Infinia, it might be in third-party S3. We can basically consume them all and link them all so that edge devices can get access to a wide range of distributed data for these RAG models.
Interesting. And when you mentioned a little bit about Infinia, we talked about expanding some of the ways we manage that data. You talked about locality and being aware of what the locality of data. And that to me talks about metadata and how you do better jobs with that. I mean, to me, object storage at sort of the cloud storage way it's been provided has way underutilized the idea of metadata. It's just such a fascinating and rich way to think about how we can get ahead of these tsunamis of big data. But it's been, I think, not really developed as well as it could have been. So what are you guys doing there?
Yeah, I mean, so we've got really genuinely unlimited metadata capability built in. So
Yeah.
Infinia can kind of act like a database. So it can store huge amounts of metadata associated with each object. And that's important, right? Because a video file coming off an autonomous driving car, every frame might be labeled with metadata. So it adds up to massive amounts of metadata. But we're also adding lots of our own metadata that allows us to behave more intelligently than existing storage. So for example, like you mentioned, when you create an Infinia system, you can inform it where the instances residing. They're in site A, in data center B, in rack C, in rack unit, whatever it is. So the storage environment knows exactly where the copies of the data are being put, and therefore it can place them much more intelligently for reasons of security, for reasons of managing fault domains, so protecting data against site failure or aisle failure or rack failure, for example, and for reasons of intelligently moving the data to where it's being consumed most frequently. So you can't do any of those things if you haven't thought about it on day one and kind of built these metadata pieces into the native key space, which is exactly what we've done with Infinia. It is quite different because we've tried to build the concept of user metadata and system metadata in a huge way right into the core of the system, so we can do these more intelligent things to make our end users' lives simpler and make the whole infrastructure more efficient.
The storage becomes self-aware, and I'm going to coin a term here, artificial internal intelligence, right? It starts to become smart about itself and a little bit aware of what's going on there and can start to do smarter managing things internally.
Yeah, you heard it here first from Mike.
There you go. There you go. That's my job as an analyst, the coin terms. What else? What else? Can you wrap up, summarize Infinia for us then? How should we think about this?
Yeah, so anybody who's had their interest piqued by this presentation, I'd love them to come and talk to DDN. DDN.com is a good place to start, and they can go and click on the button that says talk to a technical expert. And we'd love to talk to you about Infinia. As I said, it's new on the market. It is being deployed now at very large scale. So it's real, it's on the market, and it's fully containerized, elastic scaling. Use it as a service. Many features we haven't mentioned. We haven't talked about multi-tenancy. We haven't talked a lot about how we manage structured data in here. But we're really trying to resolve those challenges, broadly speaking, that we talked about right at the start. Data is distributed. Data is heavily applied to metadata. Data is being shared with shared infrastructure. And we also need to maintain that maximum efficiency that NVIDIA keep trying to pursue, which is their accelerated data paradigm, improving the hardware, but making it more interconnected and providing software connections between the layers of the storage stack in order to make the sum greater than the whole, if you like, and get more out of the hardware than it's possible from hardware alone through these optimizations.
Yeah, I mean, there's no doubt that Exascaler and the H100s and the other GPUs that NVIDIAs are making in that super pod concept are nailing the core of this AI challenge. But it's got to be connected to the greater world of the data going in, the models going out, the databases, the facts, the applications, and so
new applications.
Yeah, the Infinia. So we got Infinia here as the latest and greatest support for AI in the world from DDN, and tell us a little bit, maybe wrap it up for us, CJ, on what you look at from the data center perspective with BlueField.
I think that what we've talked about today, there are many different PhDs worth of research here, right? There are a lot of uncharted territory. And it's really exciting for us to work with other innovators in sort of working things forward. I grew up in Tanzania, and there's a Swahili word, twaweza, of we can do it together. I think there are a lot of opportunities for us to work with our partners in figuring out what are the key problems. How can we make an easy on-ramp? How can we bring new tech to bear and get the best efficiency out of these massive resources of these new data centers in the cloud and in the enterprise? I think there are lots of great opportunities here. We've really enjoyed a great working relationship over time and look forward to a lot more.
All right. James, if someone wants to learn more about SuperPods and Infinia and BlueField and stuff, where would you point them at?
Yeah, we've got a lot of materials for you to read, videos for you to look at ddn.com. You'll see a little AI button in the corner. You can go and look directly at that, and you'll see about how we provide systems to integrate storage into NVIDIA's SuperPod environments, base pods, SuperPods, and cloud systems with NCPs. You'll find it all there. Reference architectures developed over 5 years in conjunction with NVIDIA. Lots of detail, but also some great customer references as well for people to peruse.
Thank you, James, for that. Thanks, CJ, for being here today. This was great. I learned a lot. There's a lot more to talk about. I mean, AI, who knew? Big topic. We could go into any of those areas. We just scratched the surface on, I think, for an hour each. But we got to end it here. Thanks for being here today.
Yeah, thanks a lot for your time.
Take it away, Dave. Back to you.
All right, awesome job, guys. That was great. I think we just don't have enough time for questions. I know there's a ton of questions that came in to the chat, and if you didn't get your question answered, someone from DDN or NVIDIA will get back to you. So many thanks to Mike Matchett at Small World Big Data, James Coomer at DDN, and CJ Newbern with NVIDIA. To steal a term from CJ, I think it was it Twalina was the term, CJ, that we all did it together.
Twaweza.
Okay, we all did it together. We could not have done it without you. Thank you so much for being here today. Thank you to DDN and NVIDIA for their support. I'm Dave Littman at Truth in IT. Thanks again for coming. We want to wish you all a great day ahead.